So in our study about differentiating between neutral atoms, ions, and isotopes, it's important to be able to first define what isotopes and ions are. So isotopes are forms of the same element, but they have a different atomic mass. So in terms of composition, they're going to be having the same number of protons, because that's the DNA of an atom, but different number of neutrons. Thus, they're going to have the same atomic number, because remember that the atomic number is defined as the number of protons in an atom, but they'll have different mass numbers. Think of this like chubby versions of the same element. So as our example, we have the three isotopes of hydrogen, or the three different versions. So because they're the same element, they're going to have the same number of protons, which means they're going to have the same atomic number, which is visible by the ones at the top of each one of the element squares. But their atomic mass, as we can see down here, will increase as we increase the number of neutrons, which we'll prove in just a moment. In our last lesson, we learned how to calculate the number of protons, the number of electrons, and the number of neutrons. So as a refresher, the number of protons is found by looking at the atomic number, which in this case is 1. Because isotopes are still neutral, which means they have a charge of 0, the number of positive protons is going to be equal to the number of negative electrons, which means we're also going to have 1 negative electron in this first isotope of hydrogen. And then to find the number of neutrons in hydrogen 1, we would take the mass number minus the atomic number, which would give us a total of 0 neutrons in this particular isotope or version of hydrogen. But let's move on to hydrogen 2. So we're going to follow the same procedure to find the number of positive protons, the number of negative electrons, and then the number of neutral neutrons. So because the atomic number is the same, that means we still have 1 proton. So if an atom has 1 proton, then by definition, it's an atom of hydrogen. Because our atoms are neutral, the number of negative electrons equals the number of positive protons. So we only have 1 electron still. But in this particular version of hydrogen, there are 2 things that live in the nucleus. So if 2 things live in the nucleus, and we know that 1 is a proton, we take 2 minus 1, so that means that 1 of the 2 particles is a neutron. And let's do the same procedure one more time for the third version of hydrogen, or hydrogen 3. So for the number of protons, we're going to be looking at the atomic number, which is still 1 because it's still hydrogen. For the number of electrons, because this atom is neutral, the number of positive protons are going to equal the number of negative electrons. And then for the number of neutral neutrons, we're going to take our mass number, which is the bigger of the 2 given, which is 3. So that means 3 things live in the nucleus. And we're going to subtract the 1 proton we know that's in there, so it's equal to 2 neutrons. You might notice that the total mass number for our 3 versions, 1, 2, and 3, are also in the label of the isotope. And this is just one of the ways we can label our different types of isotopes. But what you might be thinking, on the periodic table, the atomic mass says 1.00794. Where does that come from? How do we get such a weird decimal from these 3 round numbers? Well, that's coming up and solving for average atomic mass. But what I need you to do right now is pause the video and find your independent practice for isotopes, and I'm going to show you a few examples. In part 2, for short answers and calculations, we wanted you to name the isotope and write its symbol. So if I have atomic number 26, this means I have 26 protons, which means that this is the 26th element on the periodic table. So I'm going to have to find my periodic table on the back of my agenda or on the internet, and I see that the 26th element is Fe, or iron. The mass number then is 56. So there's a few ways we can write this. We can have iron dash 56, or we could put a 56 in the upper left-hand corner with the element symbol after it, or we can write out the word iron with a hyphen 56 afterwards. So there are 3 ways we can denote or write down there are 3 different ways we can write down the isotopes of an atom. Let's do another one together. So if I have atomic number 29, that means my element has 29 protons. But it also means it's the 29th element of the periodic table. So after referencing my periodic table, I see that it's Cu, or copper. So then I'm going to be taking my mass number, putting a hyphen after Cu, and writing 64. Or I can write down a 64 in the upper left-hand corner with a Cu after it. Or I can write down the word copper with a hyphen and then 64 after that. This last one with atomic number 17, that means I have 17 protons. It also means that it's the 17th element of the periodic table. And after referencing my periodic table, that's chlorine, or Cl. Yep, that's not an I, it's a lowercase l. So we can put big C, little l with a hyphen 37, or we can put a 37 with a Cl after it, or we can write out chlorine with a dash and then 37 after that. So again, we're working with these whole numbers, and these are different versions of all the listed elements. But how can we figure out the decimal that we see on the periodic table? Well, that's something called solving for average atomic mass. And we're going to teach you how to do average atomic mass through this problem in your practice. So the average atomic mass is a weighted average of all the different isotopes of a particular element. And you're familiar with weighted averages because your grade is a weighted average of the 4 criteria for IB, where 25% of your grade is criterion A, 25% is criterion B, 25% is criterion C, and 25% is criterion D. If you have friends at other schools, they might have 50% of their grade is worth their tests, 30% are their labs, 10% are quizzes, and 10% are homework. So it would be an entirely different formula. So because different schools have different formulas for grades, we have to take that into consideration also for average atomic mass. So there is a skeleton formula, but every plugin is going to be different. So the way you solve for average atomic mass is we're going to take the percent abundance of the first isotope, and we're going to multiply it by its mass. And then we're going to add it to the percent abundance for the second isotope times the mass of that particular one. And then because in this particular example we have 3 isotopes, we're going to do this 3 times. So this red line is going to be representing our first isotope. The green is going to represent our second. And the blue is going to represent our third. So one thing to note, that when you see percent abundance, this is what it is in a percent. But percents are not numbers. So what we have to do is we have to move this decimal place over 2 times to make it into a number. So instead of having 99.762, our number is actually 0.99762. To move this over 2 times to the left, that means we're converting our percentages to numbers. So even when it's in a decimal, you still need to move the decimal point over 2 spots so that it's a true number and not a percent. So we're going to take the percent abundance as a number for the red isotope, or Z16. And my percent is 0.99762. And you see that I have a mass number of 16, but I also have a more precise mass of 15.995. When in doubt, always use the more precise or accurate number. So instead of 16, we're going to use 15.995. So this number that I just highlighted is my percent abundance as a number. And the second number, its mass, is the decimal version of that particular isotope mass. Then we're going to work on the second isotope. So I'm going to pull my number down to 0.0038, and I'm going to multiply it by the decimal version of the mass. So 16.999. So the number I just highlighted comes from the percent abundance as a number, and then the second number is the decimal version of the mass. And we're going to do this one more time. So the percent abundance as a number for our third isotope, or Z18, is 0.0020, because it's not 0.2 as a number, that's a percent, so that's why we move the decimal place over 2 spots, times 17.999. So the third isotope's percent abundance as a number is the number we converted earlier, times the decimal version of the mass. So if you can do this in your head, I'm really impressed, but you are going to need to find a calculator. So taking out your trusty calculator, you're going to do 0.99762 times 15.995. And for this particular activity and problem, you're going to want to write down all of the digits so I can give you partial credit if necessary. So the factor of this particular section is 15.9569319. So I multiplied these two numbers together and got this as my answer. And then I'm going to add the next factor. So 0.0038 times 16.999. And I received a decimal this time of 0.06459962. So this number is the answer to this green problem. And we're going to do it one more time for that third isotope. So 0.002 times 17.999. And I get an even smaller decimal, but it's important to write down all of the digits. So 0.035998. So this answer I just highlighted is the answer to this blue multiplication problem here. So now it turns into an algebra problem where now I'm just going to add all those pieces together. So I'm going to take 15.9569319, and don't cheat yourself out of any digits, plus 0.06459962, plus 0.035998. And I get an answer of 16.0475261. So now that we have our final answer, we can round to 2 or 3 decimal places. So we can round that to 16.048. And because we're talking about atoms and the masses of atoms are not in grams, they're in AMU. AMU is my unit. So we just solved the first part of this problem. We used the table below to calculate the atomic mass of element Z. The next portion is using the periodic table to identify the element. So just like we did with density, we came up with an answer, and now we're going to compare our experimental value to our known. So I'm going to look at my periodic table, and I'm going to find a mass number that's close to 16, and the closest to 16 is oxygen. And then that would be my answer. Now, I understand that average atomic mass is a hard concept, but you guys are really smart, and I know you can do it. So try the next problem on your own, and then check in with me to check your answers when you see me next.